Okay, let's get started. So today we're going to introduce a couple of new new like keywords, I guess, or new types of joins that'll help us to answer some more complex questions or different types of questions. And I believe this will basically bring us to the end of like the learning SQL part of the class. Okay. All right, you guys ready? Okay. So homework was due. No, homework was due yesterday, and then the next one is due on Monday. Is that right? Yeah. Homework's due. Next homework is due on Monday. This is harder than the last homework, but it's still shouldn't be. It has some more interesting questions in here. So if you haven't started, please make sure you do. All right. Last lecture, I talked about joins for the first time, and I sort of illustrated how group by works. So these are like two of the components that are really helpful in doing more advanced queries. Whereas we started off the class doing some very simple queries that were just like filtering a table and looking at the different rows. So once we introduce joins and we can connect different tables, it gets to be a lot more interesting and a lot more complicated. And the same thing goes for grouping. Yeah. And yesterday, the joins we were talking about are actually inner joins, technically, and today we're talking about outer joins, which are different. But if you just use the word join in a query, it means inner join by default. Okay. So you don't have to write inner. You can just write join. But to use the joins that we're introducing in this lecture, you have to say something before join, like left join or cross join, something like that. So different variations of joins. Okay, so last lecture we combined rows from two tables using a join predicate, which usually specifies that two columns have to be equal, and that kind of lets you cross-reference values from one table to another. And then we even joined in 3 tables and 4 tables to kind of start from one table and just expand it by cross-referencing more and more tables. Yeah. And once we add in more than one table, we have to start referring to columns as table name.column, especially because that column name could be repeated in different tables. Yeah. So otherwise you get an error that says that it's an ambiguous column name, meaning it doesn't know which table to get it from. We also use the as keyword to give an alias for a table so that we could, especially if we're using the same table twice, which is possible. If you're doing that, you need to actually have 2 different names to refer to like the first copy of the table and the second copy of the table. So you use as to give a temporary name or an alias to a copy of a table. Okay. Yeah. Any questions about that before we move on? All right, let's go then. So here's a review of what we did last time. We had like 2 different tables. As an example, staff and department. And if we want to print out a staff, like more details about these staff members, that includes departmental information from this other table, like we want the name of the department and not just the ID, then we have to join these tables to cross-reference these numbers, these ID numbers, into this other table to get the details about that, this reference here. So in this case, we did select star from staff, join, department, and then we had to say how to match the rows from one table to the other. That comes after after you say the second table name, so table 1, join the second table, and you say on some condition that has to be true for each pairing of rows in order to include them together. So in this case, we combine rows when the staff department ID is equal to the department.id. So this number equals this number, and see that's true all the way down this table. And that's basically how we match things up. This rule here in the on is the rule that has to be true for the matching to happen. Yes?
Does the order matter at all? If I wanted to switch to staff department ID?
In this on statement, it certainly does not matter, because all this is it's a rule or a predicate that's evaluated for every pairing. It comes out to either true or false, and this will still come out to the same true or false value regardless of the ordering. You might also ask about the ordering of these tables up in the first part of the statement. That doesn't really matter either, except that the only time when it matters is if you say select star, the database engine has to decide like what to print first, and it'll print whatever the first table first, and then it'll print the second table. So like these could be in a different order if you listed these differently, but that's not really a big deal. The same basic thing would happen, and you'd get the same data. Okay. Another thing we mentioned last time, kind of almost accidentally, was natural join, which is really just a shorthand notation. It's not strictly necessary. It's not a different kind of join. It just allows you to do a join without an on predicate if you happen to be using column names that have the same name. And that's often true, especially if you design your database correctly. And then a lot of the examples you'll be working with, you have already worked with, like the recipes and sales orders and entertainers. The same column names will be used. So like orders has an order number column, and then order details has an order number column. To join those together, like if you want to cross-reference the order details with the more information that's in the orders table, you can just say select star from orders, natural join order details. And we're substituting replacing this whole on condition that says how to match rows with the word natural before join. And like it says here, it just looks for whatever columns have the same names, and then creates an equality rule for those columns, right? So this allows you to make some nice short queries, because eventually we're going to start to have queries that are like 8 lines long. It just gets really messy and somewhat hard to understand. Anything we can do to make it shorter makes our life easier. So, but you can only use those natural joins if your data model was sort of designed naturally, in a sense that you're using actually the same column names in places where you have foreign keys, which are these references. So these databases I gave you are designed in such a way, like for example, it says product number here and it says product number there. It's spelled the exact same way. Wherever they're like employee ID here, employee ID here, it's spelled the same way and it can match. One thing that you might do is, like in the employee table, it might make sense to just have a column that says ID instead of employee ID. That would make it shorter. But then that would eliminate your ability to do natural joins with other tables. So like the way that these tables are designed, like there's a lot of, it's kind of redundant actually. Like the names of the columns include the name of the table kind of in them, which makes them longer. So in some sense, it's wasteful. It makes your queries longer just to say the names of the columns, but then it makes it easier to do natural joins, because you don't have generic names like ID. Like you could have ID here, ID here, ID here. Maybe not there, but ID here, ID here, ID here, ID here, and it referred to like different types of IDs, like a vendor ID, category ID, employee ID, and customer ID. That would be valid. That's actually pretty common. But then when you're joining, if you're joining these two together, for example, you couldn't. This other table wouldn't, like ID would be ambiguous, and you wouldn't know how to match it with that one, if that makes sense. Okay. Anyway, so new topic for today: cross joins. This is a type of join where actually there's no rule to match up rows, but you take every row from one table and you match it with every row in the second table. So in mathematics, when we talk about sets, this is called a Cartesian product. So if you think of the tables A and B as being sets with in this case, two rows or two values, the Cartesian product is a combination of everything from the first one with everything from the second one. So in this case, we took like dog. These represent rows, but the dog row is combined with both the turkey row in the other table and the milk row, and the cat row is combined with both the milk row and the turkey row. So you start off with 2 rows in each table, and you end up with 4 rows in the result. 4 times 2. 2 times 2 is 4. And if this had 1,000 and this had 1,000, you'd have 1,000,000 in the cross product, right? Because it would be 1,000 times 1,000. Every one of those rows would have to be matched up with every one in the second one. So and the way you write this is like select table 1 cross join table 2, for example, select orders cross join order details, or in this case it'd be like select animal cross join food or something like that, if this is an animal in a food table. It's not terribly common because you'll see, as you can see, it creates a lot of output. Like you go from n and m elements to n times m elements, which could be really inefficient. But for certain kinds of queries, it's actually exactly what you want to do. Yeah.
So this goes in the select, right, not in the from.
It goes in the from, just like the other joins. So remember, when we introduced joins, it was a way to go from. It's a good question. We started with one table initially. We want to start using multiple tables. Joins let us use multiple tables. So we replace the from. Yeah, this actually is a bogus query, which was why you asked. Yeah. This should say, should I correct it during class? Select, star from orders cross join order details. Yeah, that's what I meant to say. Instead of specifying one table, we're specifying two tables with a cross join in between. Okay. And that this is a virtual table that's created from the two tables by doing a Cartesian product of the rows. So we end up with a ton of rows. Every possible combination of rows from the first with rows from the second. Okay, so let's set that aside. We'll come back to that. There's not a ton of cases where we use that actually, but we'll have one example in class, and you'll have an example probably in homework. But let's come back to just joins in general. Remember the on function. And the function is the wrong word maybe, but the on expression, when we're doing an inner join between, let's say, orders and order details, on specifies how matches happen. We can actually think of that equivalently as taking a cross join of those two tables and using a where expression. So if you take every possible combination of rows from orders and every row from order details, and you filter out those that don't have this matching, right? That's kind of the same thing. So these are equivalent semantically. Like they'll output the same thing, and you can make this like. To make this more general by saying select A from, table A join table B on where condition, or sorry, on some condition. That's the same as select A from table A cross join table B where same condition that you used in both cases. Because you build out the full combination of all possible combinations and you throw out the combinations that don't match. That's the same as what we said, how instead of kind of like picking out the ones that do match, you start off with all of them and throw out the ones that don't match. But the second one is less efficient generally, and also is a little bit harder to read. So I'm not saying that you should do the second instead of the first, but if you understand what cross join is in terms of the Cartesian product, then this two-step thing of doing a Cartesian product and then filtering might be a way to understand how inner joins work. Yeah. Okay. So inner joins are just one type of join that has a matching predicate. There are other ones which are generally called outer joins, different types of outer joins, and these are different than cross joins. Cross joins is a separate category altogether. But even among the SQL joins that have matching predicates, that have on conditions, in other words, inner join is just one. It's the most common one. It's one where, like I said before, you construct a table of all pairs of rows where this condition is true. There's some on condition that has to be true. And all the other rows that don't match anything from the other table are thrown out. But we actually, there are these other variations keep rows that weren't matched. So this Venn diagram, the middle part of the Venn diagram are the rows that matched. And then the outer part of the Venn diagram are the rows that didn't match anything from the first table, the rows that didn't match anything from the second table. Okay, so sometimes we want to do matching, but still keep rows that didn't match anything. And that's what outer joins are. Okay, so like the simplest one is a left join. So this is where you include all the rows from the first table. So you're cross-referencing with a second table, but you're still keeping the rows from the first table that didn't match anything. Like for example, if you had staff and you're matching it up with a department table, and one of the staff happened to have a department ID that like wasn't valid, or just some bogus department ID, if we're doing an inner join, then you're only going to keep the ones that do match. So actually, you would lose that person in the inner join output. If you wanted to keep that person but just have like missing details because you weren't able to do the join, then the left join is useful. Okay, and I'll show an example that gives more concrete. Gives an example of like what that really means. So with a left join, you're going to have some rows that have null values from the right table, the second table, because no match was found. Null just means like there's no value available. And so you use left join when you want to supplement a table with additional information that may or may not be available for some of the rows. Okay. So yeah, here's an example I was telling you where we had staff members, and they have a department IDs, and you want to print out like the staff members and then also the details from the department ID table. So again, we're joining because we want to take these department ID numbers and get more details from them. We want to cross-reference, but there happen to be some people that have either like a null department or some bogus number for their department. So for these two people, Betsy and Frank, in inner join. The join in general is not going to be able to do any match, right? Because those values are not present in this other table, right? But if in our output we still wanted to include those from the left table, even though there was no match, we would use a left join. Okay, so here we have all the people. For those which did have a match, we have information from the second table, but there are a couple here that have no matching information from the second table, no rows satisfied the on condition from the second no combination of that first row of the row from the first table and any row from the second table could match this condition. Therefore, there's no matching data for the second table. That makes sense? Okay. And the way you write it is you just add the word left before the join, and that changes the way that entries from the first table that don't match are treated. It includes those rows. Yes.
Is it like kind of better practice to default to a left join then, or some sort of outer join when you're doing this?
Yeah, it might be a good practice to default to left joins. And then if you start to see null values, investigate rather than starting with an inner join and then potentially losing data and not knowing that you've lost data. Yeah, so that's probably a good recommendation. A left join is similar. Basically, when I introduced joins and I said that joins were a way of cross-referencing, that use case is really one where you probably want to use left join and not just inner join. Yeah. So yeah, theoretically, I could teach this class where we started with left join, and then later on we did inner joins. But then the fact that inner joins are the default kind of join suggests that maybe we should start with that. But anyway, yeah. So left joins are an important option. Okay. So one of the things to be aware of when you're doing left joins is that with grouping is that sometimes you get weird results for counts with left join and grouping. All right, so particularly when you're doing an aggregation of a many-to-one relationship. So, for example, if we have orders and then we have order items, so there are many order items in an order. These are like the line items in the order, right? So you might want to do like a left join between orders and order details. So, actually, do I have a? I don't. Let me write it out because I don't have a slide for it. For example, we have order like the order number and then like the product name. Let's say we have like the customer name these come from two different tables. Like you have an order table that has the customer name and the order number, and then you have an order items table that has like lots of different rows that indicate all the different products that were in that order. That's a situation where you might want to do a left join. And in this case, like you might have customer Bob with order 1, customer Bob order 2. Oh, no, sorry. Order 1 again, but there's a different product. So like first there was a bike, and then there was a helmet. These are all part of the same order. So like a left join might do this. There might be another customer Sally that does order 2, and actually but that order doesn't actually contain any items for some reason. It's like an empty order, whatever that means. So this product name might be null here. So if this is what you get with like a left join. If you then aggregate these by counting, for example, if you want to count the products, count of product name, if we just did count star, that's blocked. Let's put it on this side. Actually, it would be a different table. If you grouped by the order number and counted, you would get 2 for this one, and you get 1 for this one. That's what I'm trying to get at. You would get 1 if you counted the number of rows after the left join for this product, even though there's nothing in the second half, because there's still one row, it just has empty values on the right-hand side. And if you wanted to print, and that might not be what you want, so you can add to the count statement the name of a column, and then it counts up the number of times that column is not null. And this will let you get, in this case, the, this is a different example. In class scheduling, if you want to count up the number of classes taught by each faculty member, but some faculty members don't teach any classes. So you start off with the faculty, and then you do a left join with like all the classes. So faculty, natural left join, faculty classes. Notice that I could actually throw natural in there, and that works. But and if you group by staff ID, that condenses all the classes for that faculty to one row, and you can count up the classes. But if you had count star instead of count class ID, you would get 1 for the faculty members that are teaching no classes, because they still have a row, but it just has a null value on that right-hand side. Yeah?
All right, so just to make sure that order, if you're counting order here, it'll do it.
Well, it'll give you 1 for this one and 2 for that one. But if what you want is actually a count of the number of times that there are product like line items, if you want the number of line items, then which is probably what you'd want, because the count of order for Bob's order would give 2. The count of order for so that 2 means the number of products actually. So what we're counting is probably the number of products. So that wouldn't really be a useful thing to ask for. You should instead ask for a count of product name, because we know that value is going to be null for the ones that don't have any matches, because it comes from the second table. So in this case, we did a count of class ID because that's the thing that came from the second table, and it's sometimes null, and therefore allows you to get to 0 for the count. Even so, basically, you have to be careful with aggregation and group and left joins, because sometimes you have the left join makes you include rows from one table where there are no rows from the second table, and sometimes you want to count the things in the second table, but then show it for the entry in the first table that didn't match anything, which is tricky. Yeah. Okay. So again, these Venn diagrams are showing something abstract, which is the rows included from one table and the rows included from the second table, and in the middle are the rows that have are the rows that match up from the two tables. So right join is similar to left join, except it includes the rows in the second table that didn't match anything from the first table instead of the first table. So it's like just the reverse of right join is basically the same as left join, except the role of the two tables is reversed. So you keep everything from the second table instead of keeping everything from the first table. And you actually don't need a right join. You don't need right join because you could always reorder the tables. And so in fact, I believe that SQLite, for example, doesn't have right join, it only has left join. And if you want to implement a right join, then you should reorder it and make it a left join. Okay. The other variation of these joins is the left join with exclusion, meaning that I want to actually, so if I only want this left side of the Venn diagram, that means I only want to print out the rows that don't match rows in the other table. Which is kind of weird, but for example, if I wanted to print out all the faculty members that are not teaching classes at all, one way to do that is to do the same query from before, select star from faculty, natural left join faculty classes, but then filter out based on a value, the value coming from the second table, which is class ID, requiring that to be null. And those null values will exist because it's a left join, not an inner join, and that'll just print out those faculty. They're not teaching classes where there wasn't a match, basically, which is the left side of this Venn diagram. And then another example here, which classrooms are unused. If you take the classrooms and you try to cross-reference that with the classes that would use those rooms, if you do a natural left join, it'll print out all of the classrooms and then all the classes. There could be multiple classes per classroom, but there also could be cases where we include a classroom because it's a left join even though there's no match in the classes table. Then this where condition at the end forces us to keep only those entries where there wasn't a match. So where class ID equals null. We're checking that a value from the second table is not present. Yeah. I think this will become more clear with the examples we're going to do. Okay. There's also a full outer join, which includes both entries from the missing entries from both tables, which is not commonly actually implemented in database management systems. You can kind of emulate those with two queries and combining the results, which you do with union. We'll talk about union later. So in reality, these three on the left are available, and you can simulate these other two, but actually you can simulate all of them in different ways. Okay, so to get a feel for left joins and how they're different than inner joins, we're going to do a couple of examples. We're going to write some queries. So this first one is from the sales order table, and it's asking to list all the products and the dates for any orders. So products comes from this table here, products obviously. We want to list all those out and then cross-reference it with orders. And the order dates come from this table here. So it's actually 2 steps away. So you have to actually cross-reference products with order details and reference that with orders. So 2 joins there. And then finally, you want to actually only you want to count up those orders, or sorry, no, you want to print the dates for those orders, but you don't want to drop products that were never ordered. You want to include those in the list, but somehow just indicate that they weren't ordered ever. Okay. So let's try to do that. Get another tab. Where's my mouse? Don't see it. Where's my mouse? Help. Hold on a second. So irritating. Okay, finally. Yeah. Okay, so we want to be in the sales orders database. Okay, so remember the question. was to list all the products and the dates for any orders. We can start off by listing all the products, right? Select star from products. Easy, right? But we want to list also the order dates for those products, right? So we want to cross-reference from here back to here. Okay, so we have to do 2 joins, right? So what is products going to be joined with? Yes. Order details. Okay. So we replaced a single table with a join of 2 tables, right? So let's just do join. Let's do natural join order details. Okay, so when I run that, I get suddenly like 4,231 results. And so it includes both product information and information about that particular order, like how many were ordered in that order, stuff like that. But notice that this number will change if I use left join or regular inner join. So if I make it left join, actually it was the same. Oh, I think that this database doesn't have any products that weren't ordered. So let me go in and add a product. Item number 41 is a pencil, which has a price and a quantity, and it's in some category, whatever. Okay, so this is now a new product which has never been ordered. And again, the natural join returns 4231 rows, but the natural left join returns 4232 rows. So at the very bottom, somewhere, I guess it's a little far to scroll, but let's order by product number, descending. All right, so yeah. So since I reordered it, you can see that for the pencil item, on the right-hand side, there are these null values because when it tried to join it with order details, it wasn't able to find any rows that matched. And but it's still, because it was a left join, it still kept that value. If I removed the left and ran it, then it would throw that out and it would go straight to that first item that did have a match, which is this next one. Okay. Okay. And to complete this, so that's the crux of why this is an example for left join. We want to include that pencil item even though it wasn't purchased. And to print out the dates for the orders, actually, we have to refer back to this orders table. So I'm going to do a join between this join this join table to this other third table, right? Let's add a third table into the join sequence. So basically, I can just add another. I can add another join, right? Like join, natural join orders, right? But when I do that, there's actually a problem. So I do get the additional information, like this order date, ship date, customer ID, employee ID. These last 4 columns come from that third table. So I'm getting additional information by joining in, like, first table is here, second table is somewhere in the middle, the data from the third table is on the right-hand side. But I no longer have that pencil product listed. Does anyone know why? Anyone else? Yeah. Yeah, but why? But I have natural left join here. So why do I need it here?
It's like a new table that you have to join the orders again.
Yeah. So we can think of joins happening like step by step. So first we join the first 2 together, and by doing a natural join, then we keep the items from the first table. Well, then this second join is a join of this first result, this like virtual table, with the second one. And if we don't say natural, then it'll throw out the cases where, because remember before, the pencil item would have had null values for like the order number, and that order number is what's used to join with orders, and so it won't find a match there either. So we need to make sure that these are both left joins, and in which case the pencil has that information. And if we just want to reduce it to what it asked for, we can just print the product name and the order dates, I think. All right, so this is what it was asking for. A listing of all the products and all the dates that they were ordered. But we don't, in this case, we wanted to keep pencil even though there was no order date. Right? I mean, I don't think we can boil it down to as simple a rule as that, but you should think about the joins as happening step by step. Another way to do this would be if you actually use parentheses, you could change the order of the joins. So, for example, if I take that second join and make it happen first, sorry, not there. If I take order details and do a natural join, just an inner join with orders, I mean, that can happen without left, as long as it happens first, right? So it's taking every order detail and supplementing that with the order information, like who was the customer, when was it shipped, that kind of stuff. Those will always match. We'll never have order details that don't match a real order. The parentheses make that happen first, and then I take that whole result and do a left join with products, and that'll work. Yeah, I just need to give this. It became ambiguous, but that's not a big deal. Yeah, so this still included the pencil. So I have one left join, but just understanding the order of operations helps to get the right answer there. Okay. Yes. Well, the natural part of that query changes. It creates an implicit on condition to specify how the rows are matched. So remember here, when we do natural join, it's true whether it's an inner join or a left join or whatever. Whenever that natural keyword appears, that means that those two tables will be combined using an equality of all the columns that they share that have the same name. So in the example we were working on, it was like we wanted to do a join of order details and orders, and we want to do that based on actually the order number. So I could have also said just left join, but then I would have to say on like products dot, I have to specify how to match them, which in this case it's a product number equals something like that. So yeah, natural is just a way to eliminate one of these simple on conditions that matches columns that have the same name. Yeah, makes sense. Okay. So that was the first example, and yeah, so this is the simplest form of the answer. So here's another problem. Display the customers who have no sales reps in the same zip code. So customers is here, right? And employees are here. These are like the sales reps, means employees. And they both have zip codes listed. But you can tell from the language here, do not have that we're doing like an exclusion. So we want to look for matches We can match up the customers with the employees based on the zip code, but then we want to print not those that have matches, but those that don't have matches, right? So how would we approach this problem? Any ideas? It doesn't have to be right in one step, just a start. Let's try to just do a why is it always losing my mouse? Just do a select. I guess I'll leave that visible on the side. Display customers. So let's start by just printing the customers, right? Select star from customers. That's easy enough, you would think. So these are all the customers. So let's start by matching those up with the sales reps that correspond to the ones who are in the same location. Okay, and location is given by the zip codes here, right? So how do we match up those rows? You're gonna do a join. It doesn't have to be right the first time. Let's just try a simple join, right? Select star from customers, join employees. That's kind of weird, actually, because it's an inner join without a on statement, in which case it's kind of like a cross join. But that's definitely not what we want. Let's try. Let's start by doing a natural join, right? Customers join employees. Why is it printing out 216 rows? Are there any columns with the same name in these two tables? No. So when I do a natural join, it's not going to find any columns with the same name. So it won't do any matching. It'll just do a cross join. So you'll see here that actually every customer is matched up with every employee. So 216, I guess, is the cross product of customers and employees. So natural join won't do it. How do we want to? We don't want that full cross product. We want to just match up those that have the same zip code. So how do we do that? Yeah. Yeah. Okay, so you said left join. We'll try that. And on with that cust zip code, I'm not going to put it like the table name first because these are like not repeated, so you don't actually need to disambiguate. You said something like that, right? And that'll give it 27 results. And you'll see that all of these are cases. So you have like Susan Viescas is in zip code 98052, and there happens to be a Mary Thompson who is also in 98019. No, sorry, I scrolled down while I was doing that. Is actually the first row is 98052, both for the employee and the customer, right? But there's some in here that have no match, right? Because we included the left in that join. On the right-hand side, some of these have null values, right? Those are for all the customers where, okay, we have a customer name here on the left, but on the right-hand side, there's no employee that matched. So if we look at that Venn diagram, we had customers over here and employees here. These are the rows that matched. The ones with null values are here. There was no match from the employee table, so we just print out the values we found in the left table, the first table. Okay. So this is getting pretty close to the answer. Remember, the question is display customers who have no sales reps in the same zip code. So how do we take this and filter it down to just those who have no sales reps? Someone new. So filtering is usually done by where, right? So we have to add a where. This will, and wherever there's going to be something in here, and when this something is true, we'll keep the row. Otherwise, we'll throw out the row, right? And we want to keep which of these rows? Like of these 3 rows, which of them do we want to keep? Sorry, could one person raise their hand and tell me? Yep. Okay, that's true. We want to show the customer names up here. Like when we print out, we want to show the customer names. But actually, before we get there, we still have to figure out which of these customer names we want to print. Like we don't want to print every customer name. We want to print only the customer names who have no sales reps using this left join that we have here, right? So yeah, try again. Yeah, because and actually you could choose any of these employee type columns, but the zip code is as good a choice as any. Employee zip code is null, and actually I think you have to say is instead of equals, or you can say is. And when I run that, actually the exact opposite of what I said is true. You can't say is, you have to say equals. I think with some, like maybe with MySQL you can say is. I don't know. So when I ran this, no, it should be is, yeah. Okay, I don't know what happened that last time. Does anyone know what I did wrong? I must have typed something wrong. But yeah, so employee zip code is null is the right thing to do. Because yeah, like I was saying the first time, you can't say equals null because null is not a value that you could actually test with anything else. So there's this special is thing that you can use for testing whether something is null. Okay, so now we just have 20 rows, and these are the customers that have no sales reps, and we can just print out like the customer first name and last name from that list. Okay, and so that answers our question. See that? Okay, so that was left join. To make this all in one line, yeah, that's what it was. And survey says, right. All right. Here's a more complicated question. Show me the customers who never ordered a watch. So I have this little Venn diagram to illustrate what I mean. So if we have the customers, some of them ordered a watch. We don't want to include those. We just want the customers who didn't. But in order to answer that question, we can start by building a query that sort of matches up customers with the watch orders that they made, kind of, right? And if we can't match with a watch order, then we print that row, right? Okay, unfortunately, for some reason I got rid of the diagram because it wouldn't fit with the answers, but sorry. Customers who never ordered a watch. Let's start off with just printing out the customers. Okay. To figure out whether they ordered a watch, like which of these tables do we have to use to do that? We're starting off here with the customers. And what does that get joined to? Orders. Orders get joined to what? Order details. Order details gets joined to products. And products gets joined to categories. And in categories, there's probably a watch category. Or if there isn't a watch category, then maybe we have to look at the product names and do like a string matching to look for the word watch. I'm not sure which of those we're going to be able to do. So it's either 4 tables or 5 tables. Let's look at the database to see whether the categories have whether there's a watch category. Sorry, wrong one. There's not a watch category directly, so I guess we'll just look for the word watch in the product name. Okay. So let's start by just taking this. We'll start with customers. We already have that. And then we'll build out like a natural join just through here to get all that data out there. And then we'll actually that'll be problematic because we actually won't include the customers that didn't order anything. Yeah. How do you? There's a few ways to do this. I mean, does anyone have any suggestions for how they want to start? So the question. Remember, the question again was: show me the customers who've never ordered a watch. Let's do the opposite and print out the customers that have ordered a watch. That seems easier, right? So I'll kind of breeze through that part. If you take customers and natural join it with orders, and then natural join that with order details, and then natural join that with products. Those are those 4 tables we were talking about. And that works. It's just like for every person, it's cross-referenced to all the products that they've bought. And if you want to get the watches out of this, you can just filter, right? You just want to look for cases where the product name has watch in it. So let's add a where. Product name. Yeah, I don't think there's like actually like a watch product directly, but there's like just different products that have watch in the name. So how do we do that? How do we test for watch being in? I wonder if we can do. No, we can't. Anyway, there's like for comparisons, right? And you can use a pattern. And I don't remember how much detail we did this, but this like predicate on the third line here, product name like percent watch percent allows the text of product name to have anything followed by watch followed by anything. So it kind of like looks for just that word watch. And that includes like, I guess there's this product called Viscount Cardio Sport watch. So there are 48 of these instances where the watch was ordered. But it could be the same person ordering the watch over and over again. Like if they're Christmas presents or something, I don't know. So how would we just get the customer listed once? You could do distinct. I don't know if that's what most of you said, but there are a few ways to do it. So if you said select distinct, I mean, unfortunately, I guess you could actually say customer first name, and then you could build out the combination of the first name and last name. It's kind of an inefficient way to do it, but I think that would work. So now you have 23. I don't remember if that was different than before, but I think it was. These are people who ordered a watch. So how do we change this to get the customers who never ordered a watch? You could, like one obvious strategy might be, it's wrong, but you could try to take this check, like we're checking for watch here in the third line. You could just kind of invert that to check whether they didn't order a watch, right? So we want to keep the rows where the product name is not like watch, or I think we can say not in front. Okay, that was kind of weird. It no longer looks like English, but you can say where not product name like watch. So this would still return 27 customers. I'm not sure if that's, was it 26 last time? 23? So it'll include some of the same people, actually, right? Like Alan Davis is listed here again. All right, so this is definitely not right. Why is this wrong? What is this actually printing? What's the meaning of this query? Yeah, you were first. You give up? Yep. Here, new person. Yeah, you, the glasses. Yeah. Exactly, yeah. Did they buy up? So remember, the first 3 lines are like printing out the products, taking the names and cross-referencing with the products, and then we're keeping those where there's a product that wasn't a watch. So if someone bought anything that wasn't a watch, they would be included. But if they also ordered a watch, they would still be included, as long as they didn't order just a watch, if you follow my meaning, right? So how do we really, for real, actually answer this question? Yeah.
Join that table, like make its own table and like exclusively join it with the total customer list. So only the people that don't open the table are no longer using it.
Yeah, I think we do it that way. So we start off with this one, right? The one that was printing out the watch buyers. Okay, so this, you can use this as a subquery to generate a table, I think is what you're saying, right? So this whole thing is a table that has the names of the customers that didn't buy watches. That did buy watches, sorry. And yeah. And then you said and then say again what you were doing with it, this other part.
I guess if it has a boolean, you can do it, but if you change like the print out to the customer ID, or join everything that doesn't match that customer ID with the full customers and print out the names from that.
Okay, yeah. Was it cust ID or customer ID? Customer, okay. So we take this and we join the full customer list with this. So I'm going to need a bigger window. Select star from, let's say, customers. And then how do I join it? Yeah, so how do I do an exclusive join? I can't actually write exclusive join. There's the left join with exclusion was like where we did a left join and then we had a where clause to filter out the cases where there were null values. So actually, you start off with a left join. The full customer list left joined with this like subset list, and we want to do it based on. I think we actually do left natural join. And if we run that, let's just see what we get. It's confusing because it's there's only one output in the other table. So if we do a left join and we specify the way that we're matching is that the customers dot customer ID has to be equal to the second table's customer ID, but it's ambiguous. So we actually have to give this subqueried table a name because it's kind of like another copy of the same. It's a table that doesn't have a name because it's a subquery. So let's call this watch people. All right. Yeah, this is... Okay, so this does something, and... Okay, so right, so all the data most of the first columns are from the customer table, the first table, but the very last column, that customer ID, is from the watch people table. And there's some cases where it's null, because when it tried to do the left join, like it started off with the full customer list, and then it had the watch people table, and tried to match them based on customer ID. When there wasn't a match, because it's the left join, it kept that customer, but then it just had a null value in that from the right table because there was no match in the right table, right? So this here, like this is an example here, line 23, of a customer who did not order a watch, right? So how do we actually print out those names? We need to filter this down. And we know how to filter it because like this null value here is what we're looking for. Here. This is the key like indicator that someone didn't buy a watch. So how do I use that? Yeah. Yeah. Watch people dot customer ID is null. And yeah, I think this is the answer. There are only 4 results. These 4 people did not order a watch. Yeah, that was a good one. That was a very complicated query. And I think there are other ways to do it too. Like the answer I gave here, 2 answers. Actually, the second one is the one that uses a left join, and I think it's actually identical to what we came up with. We'll learn later on, there's an easier solution that uses except, where you can take 2 queries and kind of subtract the rows based on, subtract the rows between them from the 2 sets. So you kind of like take all the customers, the first query gets all the customers, and except subtracts out from it the result of this query, which is the customers that ordered a watch. I'm not sure which is more efficient. Maybe the first one. I don't know. Or maybe they're the same. Okay. Another one. Let's see. Yeah, we have time for another one. List the number of recipes in each category. This is actually simpler. So this is just like making sure we understand left joins with grouping. List the number of recipes in each category. Okay, so categories are here. I guess classes is really the word I mean. The classes are listed here, and for each one of these classes, there are multiple recipes. So there's like a many-to-one relationship, many recipes for each class. We want to count up all of the recipes in each class, right? So how would we do that? I got to open the right database first. Start by just printing out the recipe classes. Okay, so like these are the things we want to get count information for, like how many starches are there, how many salads, and so on. So what's the first step? What's the join we need to do? We're not just getting data from one table, we're getting data from 2 tables. These 2, right? So recipe classes and recipes. So somehow we need to join those. And if we want to count them up, if we want to like count up the number for each class, how do we do that? So if we just did a count, that would tell us how many recipes there are total, 15. But I want to break it down according to the different classes, right? Yeah. Yep. So what are we grouping by? What's the value that is like consistent within each group that we're adding? So we're adding things up, and we want within that sum, everything in that sum has to have the same something in common. And what is that thing? Recipe class ID. Yeah, so if we do that, we get the counts, and we can supplement that with like the recipe class description. Okay, so this is kind of the answer. This is a basic use of grouping. So main courses, there are 7 of them, right? Let me put this on 2 lines so we can see the whole code. Okay, so first of all, does this query producing this output make sense? Like the fact that there was grouping and then the count applied to the different groups, groups defined according to the class ID. But there's something wrong with this query. It's not right yet. If there is a class that has no recipes, it's not going to be included because this is an inner join. This natural inner join between recipe classes and recipes will throw out any classes that don't have a match in the recipes table. Right. So we have 6 rows. If I change it to natural left join, I will get 7 rows. What was missing? Let's see. Starch, soup maybe? It was soup. So let's just verify that. If I take the left out, there's no soup. Okay. But the weird thing is that soup has a count of 1, so it's telling me that there's 1 recipe in the soups class, but we know that's false because that's why it wasn't listed in the first place. So now what's the error that's causing us to get a 1 here? Still not quite right. Yeah, what do you think?
So we're counting the wrong column, right? We're just counting everything right now, whereas we should be counting, say, class, something like that.
Yeah, if we have count star, it allows us to count rows that have values in the left side but not in the right side, and that right side is where is the recipe information. So like recipe title would be a good one. If we do that, then we do in fact get a 0 for soup. Okay, makes sense. All right. All right, so finally, this query is actually really complicated and hard, and I'm going to give you 7 minutes to try to answer it on your own. Print every pair of recipes and the number of ingredients they share in common. Now remember, for every pair of recipes, and you can talk to a partner about this to try to get through it more quickly. Every pair of recipes, that's a hint that you're doing a Cartesian product, so you want to do at least 1 cross join. Cross join gives you every pair, like everything from one table, everything from the other table combined, all possible combinations. And then figuring out the number of ingredients to share in common is kind of complicated. So let's see if you can make any progress on that, and then we'll talk about it. I'm going to get some water. Does anyone have an answer? 'Cause I don't have an answer. I tried. I think I got close, but for some reason I'm getting 0 for all of them. That can't be right. But I tried to start off by taking recipes and cross-joining it with recipes to get all the pairs of recipes, and then joining that in with the recipe ingredients to, and then only keeping that only because we want to print every pair of recipes, even if they don't share anything in common, I guess. I mean, I don't have the right answer, so I'm not sure that's solid reasoning. But yeah, so I'll work this out and bring it for you next time, or post it on Piazza or something. But yeah, I think that the idea was to combine both cross join and left join. Okay. Well, just to recap. We talked about some different kinds of joins today. Inner join is the default, and it prints all pairs of rows where the join predicate is satisfied, but it excludes any rows from either table that don't match anything from the other table. Left join is like inner, but it adds rows from the left table that are never satisfied by the join predicate. Left with exclusion is where you do that, but then you actually have a where condition that explicitly throws out all the rows that do have a match, so you actually make sure that there's a null value on the right-hand side. And then cross-join is different than all of these in that it's a Cartesian product and it doesn't have any matching. There's no on condition. It's simpler in some sense. It takes every row from the first table, every row from the second table, and produces an output. Yeah, question?
How do you do left with exclusion?
It's really tiny here, but you take the same left join, you take a left join and you add to it a where condition that filters out the middle part. The way you filter out the middle part is to check to make sure that a value from the right-hand side is null. The right table is null. Okay? So, thank you.